This is a neutrino. You can't see or feel them, but every second each of us are bombarded by trillions of them. It's an elementary particle with no electric charge, and with almost zero mass, the average neutrino is less than 1/1,000,000th of the mass of the electron. It also has another name given it to by physicists, the ghost particle. Why? Because neutrinos only interact with the weak nuclear force and gravity, the weakest of the four fundamental forces. This allows them to travel through nearly everything unrestrained and in a straight line, and their minuscule mass allows them to travel at nearly the speed of light. And these properties are what makes them so useful.
On September 22, 2017, researchers at a neutrino observatory in Antarctica detected a high-energy cosmic neutrino that originated from 4 billion light-years away. This neutrino came from a blazar, a supermassive black hole at the center of a distant galaxy, blasting high-energy jets directly towards Earth. The neutrino detection facility, dubbed IceCube, is a cubic kilometer of ice with thousands of sensors that detects neutrinos by relying on the tiny chance that a neutrino collides with the nucleus of an atom. When it does, the collision releases subatomic particles, which give off a glow known as Cherenkov radiation. This glow is detected by the sensors in IceCube. Based on the incoming direction of the neutrino, researchers at NASA's Fermi Space Telescope were able to detect high-energy gamma radiation bursts from that same blazar, proving a source of cosmic neutrinos and solving a century-old mystery of where mysterious cosmic rays come from. These findings invigorated a field known as neutrino astronomy. But why neutrino astronomy? Well, let's imagine a train. How do we know that the train is, say, moving? Well, that's easy. We see it, right? But light, a form of electromagnetic radiation, which is what astronomers traditionally use, has its limitations. For instance, something like fog could block or distort light. But if we focus, we can hear the train coming. We can feel the turbulence it creates in the air. Similar to how an incoming train carries information in the form of light, sound, and turbulence, the universe gives us messages in the forms of electromagnetic radiation and neutrinos, as well as cosmic rays and gravitational waves. Neutrino astronomy is simply a different way of seeing the universe. With it, we can look at high-energy cosmic events, gaze into the core of stars, and even look into the universe the moment after it began. Physicists believe that for the first 400,000 years after the Big Bang, the universe was a hot, dense mess of elementary particles. With traditional astronomy, we can't see the beginning of the universe because light was scattered and could not escape. But since neutrinos rarely interact with other particles, these Big Bang neutrinos would have been able to free themselves. These neutrinos would be extremely weak, but observing them could tell us more about the beginning of our universe. When Galileo became the first person in human history to point a telescope to the stars, he saw the moons of Jupiter, the rings of Saturn. Neutrino astronomy is the next step in human discovery, and who knows what we'll find next. The question is not if, but when. Thanks for watching.